All right, so welcome everyone to Deep Learning Models brought to you by Eduonix. We'll be working on text classification with Keras. So that was kind of our theme for this weekend, is working with textual data. So the idea here is going to be looking at mood of people on the internet, and then the people like maybe we would interact with on social media or different review sites. So we'll be using that sentiment analysis again. And again, our goal for this weekend was to understanding how Keras can work with natural language processing problems. This is one of those more modernized things that we see a lot just because of how big data is with it being on the internet and a lot of different commenters and people joining in. So this is a link to the data. So that is a Google Drive folder with these two files in it. So if you're on a Mac, you can go through here to get to your data. And if you're on Windows or Linux, I think this should work for Linux as well. You'll just want to download the whole folder. So if you just right click on this one and then hit download, it'll download as a zip file. And then just put that in whatever directory. So extract it, unzip it, and put it in your directory. That's the data we'll be working with here. So again, if you couldn't get the data from here, totally fine. Other than that, we're just going to be doing a lot of coding today. Again, it's my last session with all of you, so I want to make sure we get everything in. Perfect. All right, so our goals for the day, we're going to start with some using the sequential model as we did in the past, and then we're also going to go into that API or the functional model as well and see some examples with that. So I'm just going to hang tight here for a minute, make sure everyone gets everything downloaded. And then we'll go ahead and start getting some coding in on my side. So first thing here, if you're looking for these first bits of code, we're going to be importing pandas as PD. Another way too, I'm going to do the imports today instead of doing it like a big dump of imports, just kind of looking through them piece by piece. So seeing, when we need something and importing it in that same cell. Now, depending where your file paths are, what you might want to do is if you are using Windows, if you just bring up the command line or command prompt is the same thing as like basically the Mac or Linux version of the terminal. If I want to see where a file is, I can just drag and drop it in here. So if I wanted to see where mine is, I can just go ahead and look for what I need and I can drag and drop it. So maybe I want to say, okay, where's this file? If you just drag and drop it into here, it'll give you the file path. And then this you can just highlight, copy, and paste. So you want everything through the C. So if it's C/users, so that's one way to find it. If you're on a Mac, you can just go directly to the terminal and do it that way. So for time of typing, I am going to go ahead and copy and paste this in of my file paths. And I'm going to leave this up for a minute here, just so everyone can get their file paths to read in that data. So these are the naming conventions. So a file path dictionary. This is creating a dictionary of what to call each one. So I have Yelp, Amazon, and then IMDb. And then the only thing of note too is if you're running Windows, it defaults with the slashes actually being the other way. So everywhere there is a slash, you have to reverse it to the other type of slash. So forward versus backwards, backwards versus forwards. And yours may look a little different than mine. I'm just going to leave mine up for an example here. And then I'll go ahead and copy and paste that in the shared file as well. So if you want to just snag that and then kind of work off that, this is probably the most annoying part of what we're doing today is reading in these different files. So if you all can let me know when you've got the file path finished, we can move forward. And I just want to make sure this is, like I said, this is the most annoying, like personalized part of this code. So once everyone's got that down, we can move on together. Another minute or two for anyone reading that in. Perfect. Okay. So what we got now, we're going to go ahead and create our data frame from this list. So I'm going to call it just df list, start as blank. And then we're going to use a for loop to read this in. So again, I was hoping today to kind of show you guys another way of reading in data, just so you get that flexibility. So no matter what kind of data you have, you can kind of do a nice, unique way of reading it in if needed. So this is a TSV file actually. So the separator here is going to be this /t for the tab. So common issue is when stuff like this gets read in, if you don't specify that the type of separator it is, such as a TSV. So if we look up here, even though sometimes is just text. So with text files, sometimes it's difficult because you have to pay attention, like looking at them to see if it's a tab or a comma. So what this line here is doing, we're reading in our data, then we're just going to specify the source that it's from. So it's going to basically create us a new column, tagging it as Yelp, Amazon, or IMDb. So instead of doing that manually with a list being merged into this data frame, we're just going to go ahead and do it all at once from reading in the source. And then here, I'm just going to say df is equal to pd.concat. We're just going to be stacking these. And then we'll go ahead and take a look here at what the first one looks like. Oh, I spelled items wrong. There we go. All right, fantastic. So what it's looking like here is our sentence, our source, and our label. So this was just reading our file path, so creating a dictionary. So the underscore dict is not necessary. I could have called this variable anything, but by specifying it's a dictionary object, dictionaries are really handy if you're reading in text files for building out data frames. So if you're ever reading a text file, it doesn't have that kind of inherent data frame structure to it. So if I wanted to look at these, where we at? So if we want to see what this looks like, this is the actual text file we're reading in here. So it's a sentence. Here's my tab separator, and then what it's being tagged towards. So the positive negatives there on the reviews. And then here's the name of it, Amazon sells labeled. So again, the sentiment analysis here, like here would be a negative feedback, do not be fooled, versus I recommend for anyone who has a Bluetooth phone being a positive there. So by reading through this, I'm recognizing that this is a TSV, so a tab separated value. So then that's our read in. And then here, what we're doing is we're creating a blank list first, just so I can put each of these spots in together. And then our for loop is for the source and file path dict. So this is my source. So the order source and then file path source, and then there's our file path. What this is doing is it's reading it as a CSV. So you can read a text file with this command. So PD referencing the pandas module, read CSV. It actually reads CSV or TSV, so tab separated values. Typically, if you're a Windows user or if you just have Office on your Mac or Linux, you see that that's coming in from, it will default opening to an Excel file. A lot of times if there's CSV, also TSV sometimes does that if you specify to open with it. But for the read-in, we use that generalized one. So file path is telling where to get the data from. The names is what I'm naming it. So I'm naming them in order. So the first thing is sentence. Next thing is going to be our label, so the 0 or the 1. And I'm telling it what it's separated on. So that /T represents it's a tab separation because it defaults to commas since it's the read CSV package there. And then I'm creating a new column in this data frame called source. So it's just copying whatever this name is up here. And then the list.append, it's putting this into the list. So it's creating myself these different lists. And then by concatenating them, I'm stacking them vertically. And then this was just looking at our first one so we could see what our data looks like. All right, what we're gonna do next here, so again, we're gonna be starting with looking at this data and then checking out what our sequential model might look like. And then again, towards the end of today, we're gonna go ahead and use that functional API as well. So I'm gonna do a couple of imports here. So I'm just gonna share these over in the shared file. So we're getting in our train test split. That one should look pretty familiar to us. Count Vectorizer we'll talk about a little bit today. So it looks at length of text, and it's an ability to turn things like textual data into matrices and numeric values, vectorizing, so that we can work at that. So we've seen that yesterday a bit as well. And then we're bringing in logistic regression. It's a handy way of working with just an example type of data. So we've seen this one before of where we read in and we ran like 5 or 6 different ones. So before we get into the sequential model, let's just test out logistic and see what it might look like. Now, I'm gonna go ahead and type out this next chunk of code here, and then we'll go ahead and talk through what it's going to do. And we will be going through this in a minute. I'm just making sure that I'm spelling everything correctly first. All right. So let's talk through this here before I. So what we did here was just a big for loop to run this test classifier here with logistic regression on each of these. So in this first part here, this dot unique basically is a nice way of using a for loop when you know you only have certain different classifications in a column. So here we had the IMDb, Yelp, and Amazon. So that means it's going to do it for each of those. So that's a nice way of ending your for loop there if you know the different sources, the different items in a categorical column, is by specifying to do it for each one. Here, it's just saying the source is equal to the source. So it's pulling that value, saying it's exactly equal to. The sentences, it's just saying look at the sentences dot values. So look at the items in there. And then here, same thing. It's saying to get the labels, just look at the label column. So these are kind of straightforward here, just defining new variables. This is doing a train test split. So we've seen this before. So we're getting our sentences train and then our sentences test, Y train, Y test. The reason why I use this naming convention here is just because we're gonna have to transform them. So when we work with natural language processing, using the dot transform feature is something that's pretty common. So we're gonna kind of see why that is just a typical thing we're gonna do in terms of how we keep on bringing that up. If you're someone who just joined us, I'm putting over the shared file there. All right, so back time to our code here. We use this naming convention only because again, I have to transform them. So I didn't want to go with I like to use the X and Y. That's pretty standard in coding. Here I just kept 0.3 for the testing thing to see how we did. And I set our random state just to keep my splits consistent. So this is where we named our vectorizer here. So what this is going to do is use the count vectorizer. So that just kind of is a good way of working with raw text data. We're fitting it. So I'm using that vectorizer to fit it using my sentences. And then same thing here with the training and the testing data. So we're transforming it here on our train and our test. So that's why I renamed these here, saying vectorizer.transform. So it's going to kind of reshape how that looks. Here, building into our classifier, we're using logistic regression. So I'm specifying it. I'm fitting it on our training data. And then for my scoring, I'm using the classifier and I'm scoring it on my testing data. And then this is just some print formatting here to make it look nice. Go ahead and run. All right. And then there comes back our output. So this is a nice way of just evaluating the model on 3 different things at once to see how it performed for each one. So what we're thinking about here is we actually have 3 different data sets we're looking to classify all at once. So this is kind of a nice way of looking at all of those things at once there and saying, okay, how can we classify if it's a 0 or 1, positive or negative based on each one? So now the goal would be here is that if we're going to go into Keras and build a sequential model or later on our API model, that we'd like to beat these results. So we should think about, okay, if we're pulling in this data, then logically our goal on the back end of this is going to be improving it. So like I always said, in the data science process here, what you're kind of looking at is you start with your more simple models and you build into something more complicated. So I'm just going to kind of leave this for a minute, just make sure everyone's, again, kind of reiterating that we always want to start with kind of our go-to simple models. So like we worked way back when we built those, that lazy predict. That was a really cool way of doing it as well by running lazy predict on our data sets. So that kind of gives you an idea of how well certain models individually are performing. And again, in real world data, that's kind of the goal. Simple is the best. The purpose of these lessons are to show you the full process of how complicated something might get. But in terms of that, if you can get, really good accuracy, if you're at above 90% accuracy on your trained test validation data with just using logistic regression or a random forest classifier, like that's really good. You might be able to get better the more complex in the layering of your model. However, we've seen a couple different approaches now to that with stacking models and then kind of evaluating them together. So the goal of this is there's not one correct way to do it. You want to kind of put your skill set and look at it as like a tiered support system. All right, but with that now, we've seen our initial ones. So like these aren't great. Like 80% is not bad if it was like some really, really complex problem. And again, the way I try to explain this to clients is that like, sorry, not clients, students would be that it depends on what you're betting on or what you're doing. So let's say I had this amount of accuracy. And I said this was going to be whether or not a stock would pay off. So if I'm going to invest in a company or invest in a stock, and if the payoff, and I said, okay, hey, I have 82% accuracy predicting that this company is either going to succeed or fail. So let's say I had 82% there, my accuracy of saying that they classified as a company that's going to be a big return on investment. How good is 82%? Well, it depends what your risk is. So risk assessment, we can go actually take some notes here. So risk assessment. So business intelligence, BI, whenever you see that acronym, whether you're on a site looking for freelance work or if you're in a company that has that on a job posting, it basically means like you have to factor in risk involved. So the way I like to kind of think about this is what you're investing. So think of, money you're saving maybe for retirement or something. So if I said like, hey, are you going to invest your entire, bank account in something with 80% accuracy? Probably not. I certainly wouldn't, because again, regardless of the type of reward there or the return on the back end, making that type of investment with only 80%, or in these models, like 70%, like that's probably not worth it. But if it was a small investment with a potentially large return, then maybe 80% is worth a try. So again, risk assessment is big, and a lot of that is understanding, the cost versus benefit to different scenarios there. All right, so let's go ahead and look at our sequential version of this. So let's go ahead and say from Karis or Karas. I honestly, I don't know the technical pronunciation there. Sequential. Then we'll go ahead and bring in our layers, and let's go ahead and create an input dimension here. So this is shaping my input data. So it's the number of features we're looking at there. So what it's doing is it's just pulling in that sentence data. So that's my input there. It's the sentence and then that tagged output there of what it's going to be. So the 1 or the 0. And then I'm going to go ahead and build out one of our more kind of standard sequential models here, which hopefully we're feeling pretty confident in building now, since we've been working this quite a lot. So again, we're using that .dense command for the fully connected. We use a 10 as our dropout. And the reason I'm going a little lower on that for this is because, again, we've got some nice data here since it's one of those nicely pre-built databases. So we can be a little more low on that dropout level. And then we'll use the 1 here. And then for our activation, we'll use sigmoid because, again, we're starting to look at that sorting of 0s and 1s. And I'm live updating here the shared file as well for everyone. So we have our input dimension, and then we can see what's kind of coming in there. So we have our 2 layers to our model here. We're doing the ReLU, and then we're doing the output layer there of our sigmoid to get the 0s and 1s. And for our next part here, we can go ahead and do our compiling. So that's where we actually kind of get the model together, right? So we do model.compile. For our loss, let's go ahead and do that binary cross entropy. Because again, we're seeing if it's going to 0 or 1, so we're classifying that way. We'll use Atom again. And then for our metrics, we're gonna look at our accuracy. So hopefully by this point, you're saying that when you're building a sequential model, this compiling step is pretty common, whether it's regression or classification like we've been working with here. If it's classification, these are kind of your defaults. And then what I want to do is take a little bit of notes here on our summary, just so we have a better understanding of that. So when we're trying to understand exactly how this is coming in, what we want to think about here is what this data means. So when we're looking through how these numbers kind of occur, how they get there. So this second number, what this one here for our output layer there, so as we say, it's sigmoid, what it's represented by is the number of nodes. So this here is the number of nodes that we have. And then here's the nodes here. So these two numbers will add together. And that gives us our number of parameters on the back end. You can see your total params comes from adding these two together. I'm gonna go ahead and take some notes here. And then this one up here actually is a little more complicated to explain. So give me a second while I All right, so getting our first one here, this 11, like we said, we're just doing the 10 plus 1 to get to 11 there. Our total parameters comes from adding these two together. And then, like I said, the tough one to get here is the one, these first ones here. So on that ReLU. So if we break it down, we first split off the 10. So by taking that 10 off, that's the bias for each node. So it's working on any like bias that the model's picking up. And then to figure out this first number here, that's where it's coming from. So 2487 is the dimensions for each feature vector. So each one of those has those 10 nodes going on it. So that's how this number kind of breaks down here. It's into a formula like this. So you can figure out your dimensions based on this output. We've already talked about epochs and batch size. We took some good notes on that. Fit our model here, we're going to be using that same understanding. So let's go ahead and get going on our fit. So I'm going to build out our history here. So before we put anything in, we'll kind of talk through a bit again how we're going to do that. So we're fitting our data. We're just calling it that variable history. You'll see it's a pretty common thing we do throughout of looking at that history variable. It's just a nice call method. Again, you can kind of call it anything. Sometimes it's just called hist, but that also gets confusing with histogram. So typically history, the full word is what's kind of common practice in Python. So when we're fitting it here, we have our training data, X and Y, so our features and our target. We haven't defined our epochs or our batch size, our verbose. We already said our validation data is just going to be the testing data there. So when we do this, what we can do here is go ahead and specify. So let's start with our epochs, maybe at like, let's start something small. Let's do 10. And then for our batch size here, maybe we want to do something a little bigger so it goes kind of fast. Let's do 50. The verbose argument, we didn't cover that yesterday. This just shows you how much output you have. So you can use true, false here. You can use numbers. For the sake of this one, just so we don't have to watch everything coming out, let's go ahead and say false. So we'll see what this looks like where it doesn't really give us updates on it. And then I'm going to go ahead and run that. So some notes here. If we're looking at evaluate, so when we're looking at this here, what we can kind of remind ourselves is we can, again, evaluate both of these things. However, the more we kind of see it go through, so the higher the epochs that we do, the more overfitting that likely occurs. So just a reminder on that, we're going to kind of look at today how we can visually see where those epochs kind of optimize at. So something else we didn't necessarily talk about yesterday is something that, again, for the sake of examples, I think we should have the full thing. So if you're doing this and you're really trying to compare different models, something that's really important here is using this method. You can kind of think of this as clearing it from scratch. So it's from keras.backend, and we're going to import clear session. So, and then we can just run the command like this of clear session. So what this does is reset all of your models. So technically, when you continuously run something over and over, it's using its previous learning. So that can involve more overfitting, that can enhance more bias into it. So we want to clear it each time. Again, this is kind of our summary point here where we're seeing the full scale idea from scratch. So we're seeing like a whole data science project and one here where we read in some data and then we're kind of comparing some different methods for it as well. So we're seeing just using a straightforward logistic regression, how we could do. We practiced reading in the data, and now we're looking at, again, kind of how to properly implement Keras. So this is actually a really important step here, is clearing that session. And if you want to make it like super copy and pasteable, I guess that's as short as we can make it there. But that would be something you want to kind of run. This is like a, control ACV, like to copy it all, copy it, paste it, each time you want to evaluate something. So that 10 coming in. That's just what this one read into. It kind of defaulted to it. So that was the 10 up front. So that was just some experimenting around with this. So when I did this, like preparing the notes for today, I played around with different dimensions here. So this first command here is specifying those dimensions. So this number is just playing around with different levels of dimensions. So that would be something, if you were doing this on your own, you'd experiment with these different numbers of dimensions. For here, let's go ahead and see how we did. Then kind of get two printouts here of our loss and accuracy. So I'm going to say model.evaluate. Then we're just going to go ahead and set that verbose equal to false. So we're going to compare how we did here with the two. What is it not like? It doesn't like my formatting on it. Where is it not liking that? Oh, forgot the colon in front. There we go. So updated that in the shared file. Forgot the colon there when I ran that. So what we can see here is, as we expected, our training data does better than our testing because, again, there's more. And we trained it over all those epochs. So we ran those 10 in batch sizes of 50. What we can see here is that we, again, see this really kind of discrepancy here. So we're only at 0.77 accuracy here for our testing data. So not terribly good. But before we go back and do anything else, let's kind of visualize how this looks. So let's increase our epochs a bit here. So I'm going to go back up here to my history, and I'm going to change my epochs to 100. And then I'm going to go ahead and rerun them. And then again, I'm going to go ahead and clear it just so it doesn't keep learning. And then I'm going to check this again. So when I turn that up to 100, something we want to notice here is the change. So I now had perfect training data. So my accuracy, I went through it so many times, was able to do it perfectly by the end. However, I now seen my testing data accuracy went down. So by running those 100 epochs, we kind of seen things change up a bit there. So this is something of concern. Whenever your training data is like really good, like I'm like 9.96, 0.97 or higher, this is where we can kind of see an issue with it because it's overfitting. So meaning it's not going to be very good on testing data. So let's go ahead here and see how we can visualize this. So if we want to see this, this is kind of a nice little way of doing it with ggplot and matplotlib. Just kind of through like looking at the number output today, we're going to learn a bit of a visual with it. So I'm going to go here and say import matplotlib dot pyplot as plt. And then I'm going to pick a style here. And there's a bunch of different style options there. It just kind of makes the graphs look a little bit different. And then right here, I'm going to go ahead and make a definition for plotting our history here. So I'm going to type it and then we'll talk through it. And sorry for the wait time here. I'm trying to really comment this out well, because one thing I find whenever I was looking up resources, people are really bad at commenting out their visualizations. Like they make it a cool looking one-liner or nice one block of code, and it's hard to figure out what each things mean, depending on how much background you have in that. So let me go ahead and just do a really good job of commenting here. Just because this is one of those you'll likely use pretty often when you're doing this type of modeling. So hopefully those comments will help you look back here on kind of how to look through that. So again, one of my biggest pet peeves is if you're ever going to contribute to like Stack Overflow or you post on things, is please comment, comment, comment. Even for me, when I first started studying visualizations, it's one of those things you can always find something similar. Like any type of problem that you want, you can find some type of online resource, whether it's a paid class or someone's post. But specifying like this command here, what this is doing is it's looking at how long our x-axis should be. So it's pulling that data from accuracy up here, seeing how many values are inputted in it. So how many different accuracies it's coming through. So the different level of epochs, that's what it's saying there. So you could just set it equal to 100. But if you do the code in this like kind of self-defined measuring way, then if you go back and adjust those epochs, it'll still be good there. Something too worthy of note, if you're ever looking at online resources, a lot of them are kind of dated and they just call this ACC. It is accuracy and val accuracy, so that was updated in the newest version of TensorFlow. In these specifications here for these plots, this is a nifty little command here. You can use the word, you could just use red, blue, green, orange. Like it's got a lot of defaults built in. If you look at PLT plot color options on a search, you can see the different ones there. I just typically choose blue and red because they stand out distinctly. And then again, the style ggplot is just kind of like a built-in styling package for how your graph should look. But there's other options there as well. And if we want to call this definition here, so I'm just gonna go ahead and say plot history, and I'm gonna call it on history. So if we're looking at these two here, I can kind of see throughout. So this is our validation. And then this here is our training versus validation loss. So what we want to play around with here, what we would like to see is kind of like, obviously these being much closer together. So we'd like to see them rise at the same time and fall at the same time. And then we're gonna see a flat line point. So to avoid overfitting is kind of wherever our validation accuracy peaks at, that's kind of where we're looking to avoid that overfitting piece to it. So what we might want to do here is go back and play around a bit to kind of get these graphs a little more readable. So again, we're looking for the peak in the red here in my validation. And then when I see this flattening out here, this is where I know I kind of went too far with the number of epochs. I'm overfitting because I'm seeing it's maxing out here. And then we're looking at the loss here. So same thing as the number of epochs increases. I want to be at the bottom of this curve. So I want to be at the bottom of validation loss. So it's looking like maybe around 20 epochs is kind of where my validation loss is the best. And I could see that as we continue to train, my loss gets lower. So as you overfit, your loss function decreases. So they vary inversely, I guess you could say. The number of epochs as they increase, our validation loss goes up, and then our training loss goes down. So if I look at that number 20, that seems to be pretty good. However, if we're looking between like kind of 0 and 10, that's probably our best bet. So 0 to 10, 0 to 20, those seem to be good measures. So let's go ahead and retrain this and try out some different options here. So if we think about our things that we can adjust way back up here, we can control our epochs and we can control our batch size. So let's try changing our epochs here to 20. And then changing our batch size, maybe let's go with something smaller. Let's try like 10. So I'm gonna go ahead and retrain that model. And then I'm going to clear it again, just so again, each time I clear it before I go back, that way I'm not overtraining again. Looking at what we get here. So we still had that high accuracy and lower training test. So let's see if we can optimize. So I'm going to go ahead and just run it again. And we're kind of seeing a different output here now, right? So we're seeing, again, that if I'm looking at these epochs here, this one's maximizing sort of throughout. So actually, I think what we needed to do there, oh, that was my bad. I should have cleared this first. So before rerunning it, you want to clear it first. So let's just do this. I'm going to go ahead and move this up just for the ordering. So let's go ahead and clear it first and then rerun it. So that, my bad, I had the order wrong there. Good, Python works. Right. Perfect. So we can kind of see that. So again, we're looking for those elbows in those peaks. So hopefully we're kind of seeing now, again, how to interpret the graph. So looking for those bends, that's kind of the key there with that. Now, I know we've done a lot with the sequential model so far. So what I want to do now is go ahead and talk about that other option. So that model API. So let's go ahead and build our node here. So I'm going to go ahead and use just a heading. And this is going to be so kind of nice to use headings in that way. So what we're going to do here, the functional model is what we can think of as another way of creating a deep learning model in Keras. We can create different layers, we can have it reused, and we can have shared inputs and outputs of data. So it allows a little more kind of advanced flexibility here. So we're going to start with kind of getting our introductory level 1, and then I'll kind of give you guys, as you've seen before, some further reading on that as you move on. So the first thing we're going to do here is we're getting our step 1 being defining the input. So we have to define what our input layer is going to be. It's kind of a standalone or singular object, and we have to identify what its shape is going to be. So let's go ahead and bring that in. So I have from keras.layers, we're going to import our input. And then right here is where we're going to define our input layer. So since we're working with that same shape of data, we're going to kind of keep it just at 1. So meaning there's just one kind of entry level, one-dimensional piece of data. In step 2, what we're looking at here is going to be creating the layers. So when we create these, we'll need to define the number of nodes. So we talked about how to define that node piece to it. And then whether or not they're going to be dense, so whether they're fully connected. So the other import we're going to need here is going to be from keras.layers. We're going to go ahead and import dense. So we're going to call this our hidden one, and then we're going to say dense. We have here our number of nodes. So here we're just going to try using 64. And then what we're going to do is go ahead and say where the data is coming from. So it's coming from my input layer. And then our last kind of structural piece to this, we want to go ahead and import our models. So from keras.layers, and I'm kind of putting all this code together because this is going to be separate from our first one. So this way you kind of have like 2 tutorials in one here. So think of this header here being like a whole different problem. So we worked with some data, now we're going to be working with different stuff just so we can kind of see how it works together. So again, the layer specification here, this would be the general way of doing that. So this is kind of our worked example here of what these layers might look like. So this isn't actually an executable model. This is just some kind of general code of what it would look like. So kind of the imports, you can see each piece to it. So technically think about that 3 pieces, the input, the hidden, and then the output. So you'll notice I didn't actually call any things like ReLU, sigmoid, any of that, linear. So we didn't actually create any real model up here. So again, this is just kind of like shorthand notes. What we're going to do now is we're actually going to build something. So I'm going to go ahead and use a heading again. So since this model is new to us, we're going to start with kind of a more visually friendly piece to it. And that's something I always suggest too when you're trying to build a new model. Never have the first time you use a model be on like real challenging data. You always kind of want to like pre-build stuff so you sort of know what the answer should be. That tells you if you're doing your modeling correctly. Because if you sort of know what the answer should be, then by default you know how to build the model correctly. It's one of those kind of like, I guess, tricks to data science is when you're learning, you should kind of already know the answer. Think of it like being a teacher in a classroom. If you're teaching something, you should probably already know what the answers are going to be. Otherwise, it kind of makes it challenging. So same thing when you're learning something, the more kind of controlled your data set can be. This is why a lot of tutorials you'll find, just like the ones we're doing together here, the ones I've created for you, are going to be working with like predefined data. So we're not collecting real world survey data. I'm not taking geospatial measurements. This is kind of pre-built data sets so we can evaluate how good our modeling skills are based on that we know we have a goal that's readily achievable. So we had section 1, kind of finishing up our work with the sequential. Section 2 right here is just this little like demo-y like sketch out, I guess, because the notes of the code. And then here, our last one is going to be our kind of full like good example of things. So how to build using the functional model API from Keras to fit that linear regression example. So let's go ahead and get our libraries here. So we're going to get NumPy. There's like a third way we've seen about doing this. So importing matplotlib, import plotplot as PLT. So again, just trying to give you all those versatility in your code. And then we'll go ahead and get one more thing from Keras. It's going to be the dropout call there. Oh, I also realized I spelled, there we go, just NP. All right. So here's something you'll see that's kind of a nifty tool whenever you're working with modeling. It's creating a space to plot to. So to do this, what we're going to do is we're going to create a sampler, a toy data set. Starting with a random seed. So to do this, the command is numpy.random.seed. And then we can just pick a number here. And then getting our points, so we're going to create some points to plot. So let's go ahead and build this out. So I'm going to type it first, and then we'll talk through. So looking at this, we're getting 50 data points between 0 and 30. And then what we're doing here for this random piece here is just putting in some noise so it doesn't come out as perfectly linear. We just don't want our data to be like an exact straight line here, which is what that linspace command does. So adding some noise kind of just builds in some fluctuation there on each side of it. Then we can go ahead and see our plot. And then how we want the data to look, so this is a nice little command here you can use for the plotting, is just that period at the end. And let me go ahead and just say plt.show here. So this plots the data that we created. So we've created a sample data set here. Just kind of looking at this of like, oh, okay, let's see what our data looks like. Here's the data that we're trying to make a prediction on. So we can visually see that this is linear data. So we're thinking that if we build a good model, it should be fairly accurate at the linear level, because again, our data looks like we could regress it fairly well. And you can actually play with this little command here if you want to make it something different. You could make it different symbols. So I can do like a minus there. If you do that, it defaults to a line. If you want it to be a dashed line, you can do it there. So that plotting feature is actually kind of cool. I think X's work too. Yep. So you can put whatever you want in there and it will plot it. So it defaults to color for some things. So kind of your typical ones are period, or you can use a plus symbol. X's for data points is also kind of nifty. But one of the defaults you'll see is the dot. So with the plt.plot command, this argument here of what you're looking in. So if you pick like a letter R, it's going to pick a red line. If you pick B, blue line, I forgot if O works. Yeah, O goes to those bigger filled in dots. Capital O does anything? Okay, no, capital O does not work. So all lowercase. Sorry, sometimes I playing around with this because I forget what the options are. So plus symbol is kind of cool. But again, play around with it, whichever one you like the best. I'll go ahead and grab those for you now. So there's the collab and then the data file. So that drive file has the data in it that we used for the first part of this. And then the collab link was shared as well. So thank you for the person who shared that as well. All right, so let's go ahead here and build this out. So let's go ahead and create our new layer. So this is again kind of that functional coding. So this looks very similar to kind of our sketched example above. I just wanted to put it all in one spot for you guys. So hopefully this example gives you a little better idea of what these layers are looking like here. So I kind of used a more formal naming convention here of the hidden 1, hidden 2, and you can kind of see that tiered input. So we have our input layer here and our hidden layer 1. And again, this is just from experimentation, looking at different dimensions with it. So how many nodes and dimensions to include in there. So that again is just a trial and error type thing. Adjust it, see how many optimize your model, and that's how we kind of get these. For the example's sake here, that's just kind of the numbers we used. The important parts of reading this type of code, so this functional API is kind of the input's a little different. It's not quite as, I guess you could say one-liner-esque or Python-y reading is when we did our sequential models. So we use that capital D for the dense command here, and then we specify the layers. So here I'm taking the input layer in. Then for hidden 2, I'm taking in hidden 1, so what it's already worked on. And for the output, we're taking that data directly from the hidden 2 layer. And then we're using linear because, again, we're using a linear problem here as opposed to a classification. And then let's go ahead here and formally define our model. So I'm going to say model is equal to model. And then I'm going to say my inputs are equal to my input layer. And then my outputs are equal to output. And then typical step here, let's go ahead and check our summary. So we're seeing our input layer has no parameters because that's just in taking our data. For our next one here, it's called dense 4, just because, again, we've used other dense layers in this tutorial. So as opposed to being just hidden 1, it's saying dense 4. We can kind of see each piece to it here. You're noticing these numbers here are matching up with the ones we chose. All right, let's go ahead and compile this. We're going to say model.compile. We'll use Atom again. And then for our loss, let's go ahead and use mean squared error, or MSE. For history, we can go ahead and say model.fit using XS and YS. And then for our epochs here, let's go ahead and use like 100. And notice, since I didn't use that verbose command specifically here, it's showing me each output, so it defaults to true. So it's showing me go through, and we can see our loss is going down each time. So as we kind of look at all of our epochs there. So we can go ahead and define a new variable here, the predictions. I'm going to say model.predict. So we're going to run that model on our data to create some new predictions here. So we're going to compare it. Oh, what did I spell wrong? That should say predict, not model. There we go. So what this is doing now is we're going to look at the actual data versus what our model would predict it to be. Then let's go ahead and get a visual for this. All right, so I put that over in the shared file. If you want to go ahead and take a look. So I just kind of moved it off my screen. So I want you guys to take a look at it on your side first and see what we think. hopefully we're kind of looking here that this looks terrible, right? So it seems like our model here didn't fit this well at all. It seems like our prediction is coming out that it should be a positive slope. We're kind of seeing a negative one here. So when we're doing predictions with numbers, that's something to always consider too, is how wide our space is versus sort of how, I guess, weird our predictions may be. So when we run through a prediction like this and we see that it, like truth like here, it makes no sense, right? We're seeing our model has basically done nothing predictive about this. So what that tells us is when we look at a visual like this for a prediction, we need to go back and adjust some things up top. So what we're gonna go back up here and do is if we go back up to here in how we trained our model. We're gonna go ahead and make this a little bit smaller here. So let's make our data set a little smaller just because we can kind of see a bit more with it that way. So again, sometimes the data size can be effective of how those epochs work. So let's go ahead and make it a little bit smaller of a data set just because I want us to have a nice model here. So let's go ahead and change these 30s just to 20s. So it's going to make our data range a little smaller. So if I rerun that, you're noticing all it's adjusting is the X and Y axis from 20 to 20. We can keep this the same. And then let's go ahead and change our epochs up to like 200 here, just to get a little more time to train on the data, just so we can get a nice accurate model. Oh, what's it not liking? Oh, forgot to rerun the compile. There we go. So something you're noticing here, by making that data smaller, we also significantly decreased our errors here and our loss. So let's go ahead and see what this is going to look like now when we run our predictions. There we go. All right. So things to consider is why it so drastically changed our model. Was it the epochs or was it the size of the data? So none of that was outlier data because again, we had this nice little pre-built data set. We defined where it was coming from. We even picked how much noise it should be and put it in there. So the difference here is not only the size of the data being a smaller window to look at, but also the fact that we ran more training on it. So when you're doing linear regression, epochs are one of those things like the more you do, the better kind of thing. So we can see here that self-correcting in the bias of the model. So at first it was predicting on a positive increase here. And then we seen it kind of self-adjust it. And it said, oh, wait, positive's not working. So at this point, we can see a clear definition of a negative space. So the reason for that is if we look at these points clustered up here in the top left, these points were kind of throwing it off because it was just going off the assumption of the positive slope there. So it's looking like, okay, positive, positive. So it's fitting based on this first part here. So it's almost fitting that model through this point. This next point brings it down a bit. And then right around here is where the model starts doing that learning piece, where it's realizing that this is going to be that negative slope. So even with the smaller window of 20 points, if I go back and change my epochs here, back to just that 100. Oh, we gotta go back and run this from the start. There we go. So if we ran it back from the start, we'd see that self-adjustment going on there as well, I should say. All right. Last thing we want to cover here, just so again, we kind of see a little more with these functional API models of the regression piece. So we're going to go ahead and build a model with a shared layer. So this allows us to share data amongst layers so they can learn from one another. And then we're going to use concatenation. So a couple of imports here I'm going to type up, and then we'll talk through. All right, so talking through what this is. So the idea of a shared layer. So instead of it being stacked kind of vertically, input, hidden, 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 here having the shared layer option allows us to kind of have our top thing, so our input layer, and then a shared layer is with essentially two kind of branches coming out of that. So these two layers working in conjunction. So notice that their size is the same here, or their dimensions. And then the results from those two being concatenated here. So merge together with the merge.concatenate. So here's that merge. And then they're being looked at by this third hidden layer here, where it's looking at those merged layers. And then our same thing, that output and then activation there. So I'm going to go ahead and compile. Also, a bit of advice is while we put all three of these into one, for best results and most readability, I do suggest at a later time combining these into or separating these out into three separate Jupyter files. So you may have to play around a little bit with the different imports because we use some common ones we used at the beginning. So playing around with those, and again, in an ideal world, you would build yourself three separate ones here. So we can see these different connections here. So we now have a connected to column that kind of shows the different connections between them. So we're getting those more complex models now with a shared layer. All right, I'm gonna go ahead and compile this. So model.compile. And we'll stick with those 200 epochs again. And I'm gonna go ahead and throw in the verbose command here just so we don't have to watch the output. All right. So let's see what our graph is going to look like now. So I'm actually gonna go ahead and pull this code from up here. Since we use that same naming convention here, we can kind of, it's just redefining those models so we can use it again. So we're noticing with these two that we're actually getting the same results. So the difference between the two is really going to come down to the specifics of the problem that you're working on. So in this case, we defined two different models, one which had these different types of layers where they were sharing information. So these two shared layers in the middle here versus these up here, where these ones, it was more of that sequential build where it went from one layer to the next. Now, in this case, since we were working with simple linear regression, we noticed that there really wasn't much difference here. We kind of had the identical output lines here coming from each. However, at different tiers of complication in your data and different tiers of your problems, if you're working with different kinds of prediction, and depending on how much noise is in your data, that's where we can kind of see these models, one being preferable over the other. By looking at these types of plots, how well they're working on that defined data. And something that you'll notice in here by building these sample data sets, what we actually did, we did our predictions on the same data that we trained on here. So inherently, we're introducing a little bit of bias there, but I wanted you to have the code blocks more than anything, just because, again, this is a bit more complicated of a method for working with these models. I'm going to try if I can see if I can find the documentation. I think I shared it yesterday, actually, the documentation on how to work through these. So building these different types of models here. So with the API calls and the functional models. So if you see functional model or API, it means the same thing coming from Keras. So the real difference here is just kind of in the defining pieces here, how we work through each of these. So what I wanted to end class with today, just because this is my last session with you guys, is kind of working through defining the, I guess you could say, like the scientific method, but for data science. So what we can kind of put together is a more formal, like, hey, like here's how to work through a problem from start to finish. because that's something I feel that like a lot of classes are missing, is the idea of like, what do the steps actually look like though, like in the real world, when we're not building training data, when we're not working through something that's sort of straightforward. So let me go ahead, I'm gonna create a new document here. And again, I'm not deleting these at any point, so you're welcome to make a copy of it. However, again, like they're not going anywhere, so you're welcome to save that as a bookmark as well. All right, so when we're thinking about this in general, so again, I'm calling this the data science process from start to approximate finish, because that's the thing with data science is, again, as I kind of spoke earlier in our work together about, is that saying you're an expert in data science in the year 2021 is a lot like saying you're an expert in medicine in the year 1800. You might think you know a lot, but in reality, like this is still a very much so evolving field. For example, in yesterday's work, we looked at something that was a published research by a team at Stanford University, and they got like 80% accuracy on their classification. And start to finish, within about an hour and a half, we got up to 88% accuracy with a pretty simple sequential model. That alone shows that from 2011, so 10-year period, a decade, just how easy it is. So going from the highest tier of expert getting over 80% accuracy to a live lecture, and with under an hour of practice, we were able to get almost 90%. So we could see that learning curve and how much it's advancing in this field. So the first general step is in the real world here. So not with the training data, is going to be our data collection. So it's figuring out where to get the data from. So from a defined question or challenge. So it's defining what it is you want to learn about. It's defining about the problem that you need to solve, and it's getting that data from it. Now, this is the cool part of when you go into data, is you may work in one or all of these fields. And in my working as a consultant, I kind of do the full spectrum of, I've handled just data collection pieces to things and manage that, which is more of a white paper, I guess, than you could say, of making sure every possible qualification is met to make sure that your data is good. It's a little more tedious and less fun than some of the coding on the back end that we often do. But that's kind of where this would start. So some things to look at in this stage of it is the idea of representative data. So representative data, this is often probably the most overlooked piece to it. And it's kind of assumed with a lot of things. So does my data look like the population I'm learning about? So in this case, we could think about things like if you're learning about, if you want to make conclusions. So in my time teaching as a high school teacher, I always said that if I want to make conclusions about the students I work with, I better not be looking at national data, because my students aren't national. They all live in the same town. So if you're looking at that, it's what your data is learning about. So specifying to what level of data you're trying to make conclusions about. So if it's a geo-based thing, if you're looking at people in a given city, you want to make sure that all the people you're sampling are from that city to make sure that you're kind of simplifying things. With that said, if your sample is from just one city, you certainly can't talk about a country or a state or anything else, because you're only looking at one city. So that idea of like polling data, same concept here. If you're going to make sure your data is representative, that's all you can make conclusions about. So we want to think about things like locations, demographics, you can say like income in there, etc. Right? So that's generally looking at people data. If you're looking at like computer things, you want to think about different kind of users, right? So throughout this course, you've seen me kind of throw in different examples for if you're on Windows, Linux, or Mac, sort of those workarounds. So that's something to plan for. If I was looking at Python implementation at large, I'd want to consider all the different user platforms. But in general, thinking about data, a lot of times we think about people or businesses. So if I was looking at, predicting, which businesses are best for me to do cold calls to, I would want to look at things like where those businesses are located, the demographics of the different companies, how much income that company has, so what's their net worth, What is their marketing margins? Where are their sales going to? Are they a national or an international company? So again, your data has to be represented. This is probably the most challenging part of any data science project, is where the data is coming from. Other things you want to think about here. So thinking about potential user errors. So ideally, you want to avoid those. So if you think about like collecting survey data, so something I've used with a lot of clients is Google Forms. It's got some cool validation features. SurveyMonkey is another big one, where you can kind of avoid users putting in stuff you don't like. You would not believe, if when you work with younger demographics, how many people like put in just like, it's like pick a number and they'll write 5 in Word. So like interpreting that. So the idea of the different way text data can come in and how you're going to work with it. Something I came across recently. So I had a company inputting ID level data. So it was a ID level data. It was 4 digits. And then for an example here, we could think of this one. So that might be one of those example digits. That came in perfectly fine. So when it converted over to a CSV, it looks great. So this one did not. So looking through the data at first, I was like, okay, we have an error here. I'm seeing there's supposed to be a 4-digit ID, and I'm getting stuff that's coming out is just 4, 5, 6. So when it converted to a CSV from the original input, it read it as a number, so a numeric value. So it said, oh, they didn't want this 0 in here. So it pulled it just as this. So accounting for user errors. Now this one was fairly easy to fix after kind of touching base with one of my clients. We're like, oh, okay, it's a 0 in front. That's why it's reading it that way. So then we were good. I just was able to change the type of text it was reading it as, which worked perfectly fine. But again, accounting for those errors and how you're going to correct them. If you get data sent out and your surveying technique or your data collection technique is flawed, you may have to resend all of that survey data. So again, the idea of piloting these things internally, think about every human error mistake that could be made. Typically, we get data from machines. So if you're thinking about like longitude, latitude, if you're pulling data that way, it's really not as big of a concern. For example, if you're measuring weights of different things, that's really, unless your scale's not accurate, it's not a huge kind of confounding variable. But a lot of data does come from people. So think about that. Again, all the possible errors that could come in, and the idea of proofing data. That's another great one if you want to look at. It's available there. To kind of get the statistical background, to look at things like sample size, confidence intervals, and then statistical significance testing as well. Looking here at data preparation. So a lot of times when data comes in, it's not in a very usable format. No matter how good your survey might be, depending on what you plan on doing with your data, you have to prepare it. So some things to think about here are your transformations and labeling. So sometimes for certain calculations, you may need to transform data. So you may need to combine it, you may need to transform it, you may need to, flip it around. So some typical transformations here in Python would be like, if you think about a general example here, df.t, so that does a transposition. So it kind of flips the data frame around there. So it transposes the rows and the columns. Some other ones that are pretty handy here in the data prep stage would be things like, and what's the other one? And crosstab. So those are some cool ones there where you can get used to group bys and crosstabs. So group bys are nice if you're trying to look at like tiered. So if I'm thinking of like a human survey, maybe I want to group by gender or sex. And income level. So if I had different income brackets people could choose from. So when we think about like census level data, those are pretty common. Crosstab is a nice thing for if you have a column of categorical values. So a lot of the companies I work with are education based. So for them, it's grades data. A lot of times the databases put out all grades. So it'll be like student A and then each of their letter grades. So crosstabs are handy for kind of reshaping that to give me a count or a frequency of each of those. So group by is pretty common when we're working with quantitative data. And crosstabs are really handy for categorical or qualitative. Oh, spelled that wrong. So those are two of the most common things you'll see that everybody who uses Python for data science uses these a lot. This one's probably like top 10. These are probably top 5. And then visualization techniques. So those are key in there. So kind of looking at understanding the data. So for things like outliers, like we looked for. So outliers, when and if we want to remove them and why. So the documentation piece. So we looked at how that's important, kind of going along of if you're going to remove something, you have to say why you're removing it. And then you always go back and run the model again without removing it. So you want to look at both pieces to that. So if I remove them, how great is my model? If I don't remove them, how bad is my model? So the idea of that is if I can run it with all this data and the model is pretty much the same, cool. I'm not going to remove any data because then I don't have to justify removing it. That's one thing that you never know when you start building a data set, what an outlier actually is. So it's pretty hard to identify outliers when data isn't necessarily large. So again, this kind of goes with the idea of how big is the population you're talking about. If the population I'm talking about is, let's say I'm doing HR data and I'm just looking at our workplace. Well, if I only have 100 employees, my population is 100 employees. I could probably go get data from most of them. I could probably get most people in there to fill out a data set so that I could really make some pretty big distinctions about what an outlier is there. So if we think about an HR example, so for here, if we have 100 total employees, I could probably sample most of them. So let's say I got 85 responses. I said, okay, we have 2 weeks to take the survey, then I'm gonna analyze it. Maybe I get 85 back. So there's 15 people that aren't there. So I want to make sure I have everything from all the departments. So if I'm missing something from the engineering department, like if I only have one person in the 10-person engineering department here, I probably wouldn't want to make any conclusions about them because they're not well represented. I'm not necessarily going to throw that person out when I'm making conclusions about the job as a whole. That's fine, but I really wouldn't want to just, use that one person from a department there. However, we could make some conclusions here about outliers. Since I only have 100 employees, if I got 85% of the population represented, that's crazy good, right? So I could make conclusions about outliers here. So I could say if one employee, for example, let's say I had 5 employees were very dissatisfied. Well, if we think about that, 5 divided by 80 out of that 85 there, that's less than 6%, right? So I could probably say, hey, you know what? If one of these dissatisfied employees is dissatisfied in everything, they might be considered an outlier, right? So it's less than 6% with the data I have. It's less than 5% of my overlying population. I'd probably say that, I'm not too worried about these dissatisfied employees because there's not very many of them and no company's perfect, right? Now, if I seen something high of those 85, maybe if I had 15 or 20 people who are dissatisfied with something, that would be a major concern, right? Because that's a pretty high percentage of people who are fitting a criteria. So again, the sample size being relative to how big your population is. And then, of course, the ever-lying important idea of statistically significant. So this is when we're working with programs here in the stat side of things. So the p-value, you'll see some things use lesser than or equal to 0.05. The standard is less than. So if it's less than 0.05, now what that means basically is that you have a large enough sample and they're different enough to say that there's statistically significant differences. So it's beyond a reasonable doubt kind of thing. If you don't get that, that doesn't mean your data is useless. Just don't say weird stuff. So a lot of times in reports, you'll see like the phrasing of approaching significance. So if you're ever writing a report and you get your statistical significance is less than 0.05, that's great. Say it's statistically significant. Don't use phrases like it's approaching significance. Like that just means it's not, and you are trying to like glorify something that's not there. So stick with the idea that if it's not approaching significance, you could talk about the data still, but don't say it's approaching significance. Don't like allude to the potential for statistical significance. Just talk about the data that you have. So even if it's not, it's still usable data, can still be informative. Just know that you're taking it with a grain of salt. Now, when we get into the predictive side, so this is where we start actually doing some things. So this kind of covers a lot of the topics we talked about. So that predictive modeling and classification. So keep it simple when you can. So we did some of those classifications here. Another one there with that lazy predict. That's kind of my go-to now ever since that was released because it just runs all of them at once. We also practice building sort of those loops to go through. So we talked about how to build those ourselves, and we've seen our different loops that we made where we compared like, a handful of models at once. We looked at lazy predict, kind of looking at all of the models at once there. So that's what I'm always suggesting to people is keep it simple first if you can. If you can use just logistic regression, you get really good results, like cool, use that as your prediction. Maybe try to build it up on the side, but a lot of times in business, it's how quick we can start learning, not necessarily how well. So if you can get a model working up that's 90+% accurate at predicting something, and it's simple, cool. Start using it with a grain of salt and then keep working on enhancing that model over time. If you're trying to make predictions on something, business moves at the speed of business, like money moves at the speed of money. The idea that the quicker you could start learning about something, the better. And again, the grain of salt idea is that like, hey, it's not perfect. It's not great. The most refined advanced model I could come up with, but it's giving us some good feedback and we can start learning from it now while I continue this background process of improving it. So those are kind of the, go-to ways there. So always going back, adjusting and spot checking your work. So when I am reevaluating a model, I actually start from scratch. So I open up a new file, a new notebook, whether I'm using Google Colab, Jupyter, whatever it may be. And then I go from scratch. I don't just rerun the same code because if I made an error in my code, chances are I'm not going to catch it if I just do shift enter a bunch of times. So getting that new notebook, trying things different throughout, maybe working with some of those outliers, seeing if I move them in. So seeing how my model performs over time, especially as new data enters. So sometimes you have to go back and retrain that model based on that new data coming in, because what may have been an outlier in phase one may no longer be an outlier in phase two because some of that new data, might be clustered around there. Maybe that's a clientele marketplace or a customer segmentation you didn't see before. And when you're building those more advanced models like we work with, whether it was ensemble learning, whether it was our sequential or the model API, functional, again, those are kind of synonymous terms. When you're getting to those levels, again, you want to kind of think about starting from scratch. So don't take all this data that you already have cleaned and moved through and then just throw it right in the model. When you get to that, when you're trying to get to that higher tier, you want to kind of start from the beginning again. You want to go through, okay, like, hey, let's review how we collected this data. Is this still all good? Do I have new data that might be challenging this? Because again, those data collection methods, as more and more data comes in, you might starting to see bias in your data. So that's the idea from going back in there. If all of your data is starting to shift to a demographic, so for example, that TikTok app, like, so I can say that every high school student I've ever worked with has that thing. I personally don't. So maybe if I'm looking at my demographics data and I'm making a prediction on something, I'm seeing a demographic shift that maybe my original data was pretty evenly segmented, but then as I'm continuing to grow this data, my data is shifting in the age difference or the income difference, whatever it may be. So again, as you continue to build out new models and add more tiers, and you always want to go back to that thought process of, well, what data am I training on? What does it look like? Because that's going to kind of affect the outcomes that I can map to successfully. So this is not an all-encompassing document by any means, but hopefully at least gives you an idea as you're working through some real-world data science problems of some things to keep in mind here of the processes to do throughout. Again, I'm not deleting this anytime soon. I apologize if there are any typos in there as I was typing it in real time. Hopefully Google Docs caught my typos if there were.